6.6, Optimization Problems Part 3, which is linear programming. The solution to an optimization problem is usually found at one of the vertices of the feasible region like we talked about in the last section. To determine the optimal solution to an optimization problem using linear programming, we want to follow a couple steps here. So first one, create an algebraic model that includes a defining statement of the variables used in your model, so our let statements, restrictions on our variable, a system of linear inequalities that describe any constraints, and an objective function that shows how the variables are related to the quantity being optimized. So we did all of those things in our 6.4 and 6.5. Part 2, graph the system of inequalities to determine the coordinates of the vertices of the feasible region. We did that last section as well. 3, evaluate the objective function by substituting the values of the coordinates of each vertex, which we also did. 4, compare the results and choose a desired solution. And 5, verify your solution satisfies the constraints of the problem situation. We have covered all 5 of those in the last section. Now we want to put it all together in a couple more examples here just to solidify that understanding. So example 1. A local craft shop produces copper bracelets and necklaces. Each bracelet requires 15 minutes of cutting time and 10 minutes of polishing time. Each necklace requires 15 minutes of cutting time and 20 minutes of polishing time. There are a maximum of 225 minutes of cutting time and 200 minutes of polishing time available each day. The shop makes a profit of $5 on each bracelet and $7 on each necklace sold. How many of each should they make per day to earn the most money? So what we're trying to optimize here is maximize our profit. How can I make the most money? The first thing we want to do, according to our steps, create an algebraic model. So we want to define our variables that we're going to use, so our x and y, our let statements here. So let's let x equal the number of bracelets, y equal the number of necklaces. Does it matter if you were to switch those? Absolutely not. Up to you. But we will say let x be the number of bracelets for now. And let y be the number of necklaces. We know we can't make half a necklace and sell it, or -3 bracelets and sell them. So we know we have x is an element of the whole numbers, and y is an element of whole numbers as well. What is our objective function? Well, we're trying to maximize, earn the most money. So in terms of profit, what values did we see talked about money? So $5 we make for a bracelet and $7 for a necklace. So profit equals $5 per bracelet and $7 per necklace. We are going to come back to this at the end after we find the points on our vertices when we graph our inequalities and check to see which one optimizes our objective function. So let's identify our inequalities, our constraints. We have our limitations stated in this question. So in terms of cutting time, if we think back to our football and soccer ball question a couple of sections ago when we were talking about cutting and stitching, our cutting time for each, so bracelets need 15 minutes and necklaces need 15 minutes, so 15x plus 15y must be less than or equal to 225 minutes. So there's a maximum of 225 minutes for cutting time, so we cannot exceed that. That's our inequality for cutting time. While we're working with this one, we might as well change it to y equals mx plus b form, so we have it ready to graph. Let's subtract 15x from both sides. Leaves us with 15y is less than or equal to -15x plus 225. Dividing both sides by 15. Y is less than or equal to -x plus 15. Inequality number 1. The next one will be based on polishing time, so I'll do that in another color. Each bracelet needs 10 minutes of polishing time, so 10x. And each necklace needs 20 minutes of polishing time, so 20y. Must be less than or equal to, we can have no more time than 200 minutes of polishing time each day. So we're limited to 200. Subtracting 10x. Negative 10x plus 200 divided by 20. Y is less than or equal to negative 1/2 x plus 10. So these are the two inequalities we're going to graph to identify our vertices where they all intersect with each other and the axes on the graph to the right, and plug those points into our objective function right here at the top again to see which one will help us earn the most money. So let's graph these two, starting with green. We have a y-intercept of 15 and a slope of -1. So using this graph to the right, going up by 2s, 2, 4, 6, 8, 10, 12, 14, 16. So my 15 will be right in the middle there, going down 1, over 1. Again, it can be helpful sometimes for us to identify where the intercepts will be. So we can always plug in 0 for y. My x-intercept is when my y is 0. So 0 is less than or equal to negative x plus 15. Add x. X equals 15 is going to be my x-intercept. So I can do the same thing here. So here's 15 if I go up by 2s. I have an equal sign, less than or equal to, so I'll connect these with a solid line. Not straight. Again, do your best with your straight edge. And I want less than y, so I want to be shading underneath this line when it comes time to do that. My blue inequality graph has a y-intercept of 10. And an x-intercept of, so we can solve for that, or we have a negative slope, -1/2. But when my y is 0, I can subtract 10 from both sides and multiply both sides by -2 to get rid of my denominator. So 20 equals x. My y-intercept is at 20. So if this point was 15, 16, 18, 20. Connecting those points to the solid line as well, as we have an equal sign in our inequality. And I also want below this line, as I have a less than. So my feasible region, the area that satisfies both of these inequalities, is here. Now we are talking about optimization, so we don't want to pick points within that area. We want to look at just the vertex of this shape. So a few of our vertices that we can see clearly here are 0 and 0. Marker quit on me. So 0 and 0. We've got our y-intercept of the blue, so 0 and 10. We can clearly see this one, which is our 15 and 0. But the one that isn't always clear, depending on how neat your graph is. So to me, 1, 2, 3, 4, 5. This looks like 5 and it's hard to say exactly where that intersects. So I went up by 2s, so 2, 4, this should be about 5. And to the right, 2, 4, 6, 8, 10, I would say. So it looks like 10 and 5. Again, depending on your neatness, it's hard to say. So there is a way algebraically that you can solve for that. We're going to write our other one as 10 and 5. But if you're wondering, yours doesn't look exactly like that, there's a way you can solve algebraically for what are my x and y values there. So your solution, your point of intersection again, is where you make them equal to each other. So I'll do that in blue here. If I want to set my first equation with substitution, they're both equal to y. So I can write negative x plus 15 equals negative 1/2 x plus 10. Since they are both equal to y, I can use substitution to make them equal to each other. Bringing the x's to one side, so adding 1/2 x and subtracting 15 to both sides. Negative 1x plus 1/2 x is negative 1/2 x equals 10 minus 15 is negative 5. To divide by negative 1/2 is really like multiplying by negative 2, or negative 2 over 1. To cancel those, so x equals 10. So that just proves that that really is 10, that point. Now to identify your y value when x is 10 is plug that value back into one of them. So our first one is y equals negative x plus 15. If I plug in 10 for that x value, what's my y when my x value is 10? Y equals 5. So that just confirms that our point really is at 10 and 5, as we kind of guesstimated based on how neat my drawing is. We did know that my lines weren't perfectly straight, but it did come out quite accurate actually. So these are our 4 vertices. These are the points that we want to be trying to optimize our profit. So in black we had our vertices of that shape, but we talked about last section that up and to the right was where we noticed the most maximized profit, was our highest point and up and to the right. So we want to check up and to the right and just check what our profit is at these points. So 0 and 0, we know our profit's going to be 0. 0 and 10, so plugging that into our P equals 5 times 0 plus 7 times 10 makes us $70. P equals 5 times 15 plus 7 times 0 is $85. Sorry, $75. Read that wrong. And our 10 and 5 makes us $85. So the furthest, the highest up we could go into the right ended up being our intersection point here that we were wondering about, that 10 and 5 optimized. So here I could either make $0, $70, $75, or $85. So this is our optimal solution here, is where our cars, our X value is 10, or sorry, wrong example. Our bracelets is what we're talking about now. Our X value bracelets is 10 bracelets, and we make 5 necklaces. We will make the most money. So we would answer that 10 bracelets and 5 necklaces should be made. Example 2. Fertilizer for a lawn comes in 2 brands as follows. So we have brand A, which has 30 kilograms of nitrogen per bag, 2 kilograms of phosphoric acid, and 1 kilogram of potash. Brand B has 20 kilograms of nitrogen in the bag, 4 kilograms of phosphoric acid, and 4 kilograms of potash. A lawn needs at least 120 kilograms of nitrogen, at least 16 kilograms of phosphoric acid, and at least 12 kilograms of potash. If brand A costs $22 a bag and brand B costs $18 per bag, how many bags of each brand should be used to minimize the cost? So minimize, what is the minimum cost that we can have? So starting with our defining our variables, our let statements. Let's have let X be number of bags for brand A and let Y be number of bags for brand B. Our objective function, we want to minimize our cost. So finding the terms in our question related to money was our brand A cost $22, brand B cost $18, and we want to minimize that. So our objective function in terms of cost is $22 per bag of brand A plus $18 per brand of bag B. So this is our objective function that we'll come back to again. We want to minimize that. Some restrictions that we have for nitrogen. So we need at least 120 kilograms of nitrogen. Well, a bag for brand A for X is 30 kilograms, so 30 kilograms per bag of brand A plus 20 kilograms of nitrogen for brand B needs to be greater than or equal to 120 kilograms, at least 120 kilograms of nitrogen. Doing the work here to isolate Y, subtracting 30x from both sides. Dividing by 20. Y is greater than or equal to negative 3 over 2x plus 6. This is nitrogen. Now a constraint in terms of phosphoric acid is 16 kilograms. So same thing, 2 kilograms in brand A plus 4 kilograms in brand B needs at least 16, so greater than or equal to 16 altogether. Isolating Y, 4y is greater than or equal to negative 2x plus 16 divided by 4. Y is greater than or equal to negative 1/2 x plus 4. And the last one for potash. We have 1 kilogram of potash in brand A. We have 4 kilograms of potash in brand B. And we need at least 12, so greater than or equal to 12. Isolating Y. Y is greater than or equal to negative 1 over 4x plus 3. Now graphing these inequalities that we came up with, so the blue one first, we have a y-intercept at 6 and a slope of negative 3 over 2. Y-intercept of 6. We can also solve for our x-intercept if we want when our y is 0. We have negative 6 equals negative 3 over 2x. So multiplying by negative 2 over 3 would be positive 12 over 3, which is 4. So x equals 4 as our x-intercept, and we can just connect those as well with a solid line because we have an equal sign in our inequality. For our green inequality, y-intercept of 4 and a slope of negative 1 over 2. Again, we could also solve for our x-intercept, or y is 0, so subtract 4 from both sides. Multiply both sides by negative 2. So I'll have an x-intercept of 8. Connecting those two with a solid line. And our red inequality has a y-intercept of 3. An x-intercept, so negative 3. Multiplying both sides by 4. I have an x-intercept of 12. And connecting those with a solid line. So, in terms of what part am I shading, they're all greater than, so I need to shade above the line for all of them. which means my area exists using these lines as its border, getting as close as you can to them without going over, and then everything up and beyond. So because this is a minimizing question, I obviously don't have a max. I can just keep on producing since we're not restrained. We want more than we have. It must be this or more. So we aren't limited in terms of our max, but what's our minimum cost going to be? Because we can continually increase our cost by purchasing more bags. We don't want to do that. We want to save some money here. So our minimum cost, we want to identify our vertices still, which will be here, 0 and 6. The ones that are obvious to us, I see here, which is 12 and 0. Again, if I had to guess, this would be 2 and 3. And we could solve just to double check. And this one with green and red looks about 4 and 2. So those are our vertices here. In our previous section, we said we wanted to look down and to the left to identify our minimum cost. So low and left. So if we try all 4 of those vertices, let's try 0 and 6. So our cost is 22 times 0 plus 18 times 6 gives us a cost of $108. Our point 2 and 3, we get a cost of 22 times 2 plus 18 times 3 equals a total cost of $98. So we're slowly lowering. Point 4 and 2, our cost is 22 times 4 plus 18 times 2. We're back up a bit at 124. And our lowest point, but to the right, is 12 and 0, which gives us a cost of 22 times 12 plus 18 times 0 is $264. So our lowest minimized cost is 98, which you can see if we go as low as we can, but to the farthest left is this point, which gives us $98. So we want to buy 2 bags of brand A and 3 bags of brand B to minimize our cost. So our final answer would be to buy 2 bags. Our X value is 2, so 2 bags of brand A and 3 bags of brand B. Your assignment is on page 341, number 1, 4, 5, and 11 to 15. Once you feel confident with this optimization content, there is a quiz 6.4 to 6.6, which is all optimization, the part 1, 2, and 3. When you've got that completed, next is your chapter review on page 349, and then your chapter 6 exam. Good luck. Let me know if you have any questions.